This question says, when carbon dioxide gas is dissolved in water, it reacts with the water to form carbonic acid. This is why soft drinks have a low pH, and soda water is often recommended as a mild cleaning agent. It is also why there is a concern that rising levels of atmospheric carbon dioxide may cause the Earth's oceans to become more acidic. Here is the reaction between carbon dioxide gas and water, shown here. So it says, suppose an engineer decides to study the rate of this reaction. She prepares 4 reaction vessels with 119.8 grams of water and 13 grams of carbon dioxide in each. So note that the amount of water and carbon dioxide is constant for each of the vessels that we're going to study. The volume and the temperature of each vessel is shown in the table below. And we want to rank them in terms of the initial reaction rate. What you'll notice is there are 2 variables, the volume and the temperature. So we need to think about each variable. Well, one thing that we have to remember when it comes to rates of reactions is that chemicals are physical things. So in order for water to react with carbon dioxide, it literally needs to bounce into carbon dioxide and for a reaction to occur. And there needs to be sufficient energy in that collision such that the molecules will actually go on to form product. If there isn't enough energy, they may just bounce into each other and then bounce off in different directions as still water and carbon dioxide. So in order to have effective collision, first we need a collision, and then we need that collision to have the sufficient energy. There's also an orientation thing that I'm not going to get into here. Sometimes the molecules need to be in the proper orientation. But here, temperature affects the energy that the molecules have and the chances of there being effective collision. Said another way, the higher the temperature, the higher the rate of the reaction. The volume affects the number of collisions. If the molecules are in a smaller space, they're more likely to collide. So therefore, smaller volume equals greater collisions. So let's look at these 2 trends. So if you look at the temperatures, we have 36 and 37 degrees here. So 37 should afford a higher reaction rate. Now let's look at the volumes. If we look at the volumes, we have 2 liters at 37 and 3 liters at 37. So in this case, 2 liters, which is the smallest overall volume, and 37 degrees is going to be the fastest. Small volume means more collisions. Higher temperature means greater fraction of effective collisions. 3 liters at 37 will be second. The next one is 3 liters again, but now it's only at 36 versus 5 liters at 36. So 3 liters at 36 is a smaller volume at the same temperature versus 5 liters at 36, which is going to be the slowest because we have the largest volume and the lowest temperature. Note that if you have divergent trends, this question wouldn't work because you'd actually have to go and do a bunch of math to figure that out or possibly even some experimentation. But here we have clear trends. So the thing with the higher temperature also has the smallest volume. When they're tied, the temperatures are different, and then at the lower temperature, it has a greater volume. So in these questions, you won't have any divergent trends.